Welcome to the finale in our series of short interviews on topics of artificial intelligence and agency. Throughout the series, the conversations have been deliberately brief, designed to respect both our guests and audience time. Each interview, however, has been accompanied by a reading list to allow for deeper exploration of themes introduced. And our guest today is Professor Karl Friston. I genuinely couldn't think of a better guest for this final session. And Professor Friston is a British neuroscientist, professor of neuroscience at University College London. Uh, he is one of the most cited scholars in the fields of neuroimaging, computational neuroscience, and theoretical models of brain. His pioneering work includes the development of the free energy principle, which has become a foundational framework for understanding perception, action, and cognition. And Professor Friston and his team are also applying his theory of active inference to the design of next generation intelligent systems. And his influence, of course, extends across neuroscience, psychiatry, and artificial intelligence and philosophy, with a body of work that has reshaped how researchers think about the brain as a predictive self-organizing system. So, Professor Friston, thank you very much for accepting our invitation.
Well, thank you for that very kind introduction. It's a great pleasure to be here.
All right. Thank you very much. So I'll start with with the most general question. So about the frameworks that you are using for the study of cognition, perception, and action, and the framework that I assume you are going to adopt today too, to discuss agency and artificial intelligence. So what is free energy principle and how you use it to explain perception, cognition, and so on?
So my usual answer to that is another question. Do you want a low road or a high road explanation? And I'll try and give you very briefly both. So the high road would be that taken by a physicist who wants to understand the self-organization of things and indeed the self in self-organization. That requires a specification of how you separate or disambiguate self from non-self. Mathematically, we do that by inducing something called a boundary, a Markov blanket. The very induction of that blanket means that you can now describe self-organization in terms of the physics of organization to technically a non-equilibrium steady state in terms of inference. Technically a kind of Bayesian mechanics that complements quantum mechanics, statistical mechanics, and indeed classical mechanics, but is distinguished because in virtue of that partition between the states of self and non-self, say the states of the universe, you can now talk about the information theory, or colloquially Bayesian beliefs, held by the internal states about the external states. And this can be read as a form of inference, a Bayesian mechanics of belief updating. And when one puts into the mix the fact that the self, the thing in question, say a particle or a person or a population, acts upon the rest of the universe, you now also have a calculus or a mechanics of decision making, of action, so thereby completing the perception action cycle. So that would be the high road. The low road would be a much more intuitive story. It's what does this kind of self-organization look like? Well, it would look like that the internal states of something, say me, my brain, for example, would look as if it was trying to predict the consequences that I can sense in terms of what caused my sensations. So it would look as if my brain was a statistical organ, a predictive machine that was continually in the game of trying to find the best explanations for the sensory impressions on this boundary that defines me, the sensory sector of my Markov blanket. And from that, you can tell a story of a certain sort, which would be Kantian. I prefer a more Helmholtzian story, say in terms of unconscious inference, that also can be framed in terms of perception as hypothesis testing, of the kind that has been used to great effect in machine learning and indeed in modeling. One example of that would be predictive coding, which has now become a very popular metaphor for how the brain works, that the brain is essentially trying to predict what it would see if its hypotheses about the causes of its sensations were correct. And of course, if it can do that, then there will be no mismatch between the predictions of a generative model and the actual outcomes, content, or sensory impressions that it was actually subject to. And that means it would look as if my brain was trying to minimize prediction error. And prediction error can be thought of, if you like, as a particular instance of the high road explanation, which would cast things in terms of free energy, hence the free energy principle. So you can think of free energy as an information theoretic description of the prediction error, the surprise, the incongruence and mismatch between what I would expect if I understood the world properly and what the world is actually impressing upon me.
Oh, very good. And we are going to put some readings, accompanying this with some readings for our audience to be able to go and explore these technical terms. But on the one hand, you started by speaking of the brain and its encounter with sensory inputs and generative models and how the brain increases the precision of its representation of the world. But through this image also emerges more sophisticated accounts of selfhood and decision making and so on. So how such sophisticated constructs could emerge from this technical account of minimization of prediction errors?
That's an excellent question. So I've talked about the general principles that would apply to any self-organizing artifact, whether it's a natural or an artificial intelligence. There are certain kinds of things, particularly literally large things with a deeply structured generative model on the inside, say, of the brain. Now, these particular kinds of things, you could call them natural kinds, don't have direct access to their actions. And the active states are part of this Markov blanket that separates me from the rest of the world. And if I don't have direct access to the active states, say my actuators or my muscles or my autonomic reflexes, then they become vicarious causes of my sensations. But we've just said that we can describe the brain as trying to represent or infer or predict the consequences of the causes that now include my own action. So this leads mathematically to a really interesting situation. It looks as if I am inferring my own actions. And in the technical literature, this would be called planning as inference. So that tells you that we're dealing with a very special kind of generative model. We're dealing with a generative model that entails my future, and specifically counterfactual futures that are determined by what I can commit to in terms of policies or actions or combinations of actions. That tells you a couple of really important things. First of all, my generative model includes the future. So there's a certain future pointing aspect. It's also conditioned upon what I do. So it's private to me. And one could argue that to be an agent is to have a generative model of the consequences of my action. The other interesting thing it brings to the table is that in that model, there will be certain imperatives that are supplied by the physics account of self-organization that will look as if they are intentions. So now we have the notion of an authentic agent that has agency in virtue of having intended states of being to which it could work towards. And indeed, you score this technically in terms of something called the expected free energy. So we just said that the free energy can be read as prediction error, and that's perfectly apt to score the quality of my sense making. I can just change my mind about the causes of my sensations, namely the states of affairs in the world at the moment, and that would be mathematically equivalent to minimizing the variational free energy. But I can't do that in the future. Why? Well, because the outcomes that I observe in the future haven't yet happened. So now I have to take an average or an expectation over or under the outcomes that I would anticipate in the future if I did that, if I committed to this course of action. And therefore, we have to deal with another quantity called expected free energy. And I mention that because there's some really interesting decompositions of expected free energy which endow agency with some specific characteristics. What one can do is divide the expected free energy into effectively an epistemic part, an information-seeking part, and a goal-seeking part that scores the quality of a course of action in terms of avoiding very surprising outcomes given the kind of thing that I am, sometimes described as prior preferences or prior constraints or prior costs. The point I wanted to make here, though, is that if you just look at the physics, if you derive from first principles, what this natural kind of thing would behave like, it will behave as if it is curious. It will behave as if it is information seeking. You can read that in many ways. One nice way is to say that, well, everything that we do, whether it's changing our mind in terms of perceptual inference or whether it's planning as inference, acting upon the world to solicit new data upon which I can base my inferences, everything is in the service of minimizing surprise or expected surprise. Mathematically, expected surprise is just uncertainty. In information theory, it's entropy. So I'm always in the game of minimizing, resolving uncertainty by acting on the world, querying the world in order to maximize the information gain under the constraints that I always secure those outcomes that are consistent, I repeat, with the kind of thing that I am.
Oh, thank you very much. Because a large number of our audience are like myself, philosophers, and because we want to make it a bit more intuitive for them, could we do a comparison perhaps? So, for example, a bacterium that is swimming up in a gradient to make its way towards some nutrients. It seems that in some way that bacterium has some goals as well. I mean, and it is also interested to explore its environment, to probe its environment, and so could we make some sort of comparison in the framework that you introduced to set a distinction between these kinds of elementary goal directedness, which are not usually considered like, are not usually understood in terms of agency, and more sophisticated kinds of goal directedness in more advanced organisms?
Yes, well, I think you've just answered your own question with that nice example of the bacterium ascending, showing chemotactic behavior. Another example would be a thermostat. A thermostat will just switch on when it thinks it's too hot, it's too cold, and switch off a heater when it thinks it's too hot. So does the thermostat have goals? I would argue not in any meaningful sense. It certainly has set points, and you could describe that as goal-directed behavior, or the behavior of the thermostat as goal-directed behavior, but it's not the kind of intentional goal that I was just talking about. The hallmark, the bright line between, as you put it, this not very nicely, it's an elementary goal-directed behavior and the kind of intentional behavior that qualifies you as an authentic agent is that the intentions are in the future and they can only be accessed by selecting among a small or finite number of different policies. And I think the use of the word selection here, and I mean this in a technical sense of Bayesian model selection, but also to intimate or to use it in the vernacular that I have to select. So in a sense, possibly at a subpersonal level, but also possibly at a volitional level, there is an an active quality of selection amongst a number of alternatives, and these alternatives are my alternative futures, which reveal the true essence or the nature of an intention. It is a state of affairs which is not yet realized, that I can work towards by selecting something, a path towards that state of affairs in the future. So that was exactly the difference between the natural kinds that I was trying to intimate when we're talking about deeply structured, or things that have deeply structured internal states, where there is no longer any direct access to the actions. For the thermostat, it would be turning on and off a heater. For a single-celled organism with flagella, it knows, the intracellular dynamics will know about the status of the locomotion and the actin filaments and the flagella that are propelling it through the world. So there is no need to infer what it's doing. It knows what it's doing, and it looks as if it's climbing concentration gradients of some chemical attractant, and it looks as if it's got a purpose, but it doesn't on the inside have any intended purpose, because it doesn't have a generative model or that is conditioned on its actions, because it doesn't need to infer its actions, it knows its actions.
Thank you very much. And the example of thermostat was even better than the example of bacterium, because this program is about artificial intelligence and artifacts and so on, and whether they are capable of demonstrating some sort of agency. So thermostats are incapable of demonstrating that sort of agency. But do you think that there are, or there could be, also artifacts that can implement genuine forms of agency in the way that you just described, in the way that it is that we attribute to sophisticated organisms or creatures like ourselves?
Yes, no, in principle, I don't see why not. I mean, we see sort of natural intelligence and natural kinds that show this sort of intentional agency or intentional behavior all around us, but not everything does. You know, and it's an interesting question. You know, at what stage does something become or evince intentional behavior? Somewhere along the line, from a virus to a bee, one presumably crosses that threshold should it exist. And I see no reason why one couldn't create artificial artifacts that have this intentional aspect, that have the capacity to plan in virtue of the fact that they have a generative model that can support planning as inference.
Yeah, but could you elaborate a bit about the properties or character? So by saying that in principle you think that there could be such systems, I gather that you mean it doesn't mean that the present forms of artificial intelligence are capable of demonstrating that sort of agency. Am I right in presuming so?
Yes, it is a delicate question given the sort of controversies around large language models and generative AI at the moment. But on the reading of agency, or at least authentic agency, as the capacity to select amongst a finite number of futures with the curiosity of expected information gain as part of the objective function, there are a few examples of that, and you won't find them in generative AI. Generative AI is just a beautiful piece of engineering that has leveraged state-of-the-art neural networks to map from content to content. It's the use of, I repeat, decades of engineering investment in applying universal function approximators to map from one thing to another thing. And in the context of, say, large language models, it's mapping from a sequence of past text to the next token, for example. So at no point is there an explicit generative model. A generative model would require a mapping between cause and content, or cause and consequence, or cause and effect. So a generative model has as part of its specification the cause-effect structure that generates the content in question, whereas things like large language models don't have that. Furthermore, and probably more importantly, they don't have agency in the sense that they don't have intentions, they don't have plans. So you'll know that a large language model has acquired agency that we associate with natural intelligence when it starts asking you questions, when it shows evidence of curiosity, when it starts prompting you, then you might start to suspect that this particular architecture, this generative AI, does have intentions, and those intentions are underwritten by this artificial curiosity or the expected information gain part of the expected free energy. In order to do that, though, in order to have an artificial intelligence that can evidence this intentional behavior, it has to be able to act. It has to be able to change the world in some way. So we're coming back to where we started in terms of the free energy principle being an account of action and perception. So there's a circular causality here that characterizes real things, including intelligent things, that requires the self or the artifact or the intelligence to be open in a bidirectional way to the rest of the universe. And being open in one direction would be perception, the outside would be influencing the inside, but crucially you also have to close that loop, if you like, that action perception loop, by the inside changing or influencing vicariously through the active states the outside. So that's the first thing you'd be looking for if you want, if I gave you an artifact and said this is some artificial intelligence and you wanted to know, does it have agency? You'd be looking for evidence that it can change the world. So your computer has to do something. And if it doesn't, it can't be an agent. And then you'd be asking, well, what are the kinds of things it does? Does it look as if it has a generative model or some belief structure about the consequences of what it does? And can I understand this in terms of the imperatives that underlie the choice that it shows when it commits to doing this or to doing that? And at that point, you'd be looking for evidence that it was information seeking, that it was curious, that it was responding to epistemic affordances, that it was novelty seeking, that it was responding to informationally salient cues in the environment by acting in a way that revealed or disclosed the information in responding to those or engaging in this kind of epistemic foraging.
All right, I have two questions about this, but I'm going to suppress them to ask a more basic question. So when I think of curiosity and this drive to explore, for some reason I think of that in evolutionary terms. I mean, something that we needed, some organism needed in order to be able to go out of the cave and start to find enough evidence for their existence and so on. What about this kind of artificial intelligence system? Is that something that is inbuilt into them, or something that they can just acquire by replicating a process of evolution or something like that? I mean, or some sort of evolutionary drives are built into them. I mean, do you think of that in some sort of ecological setting, or in terms of some sort of, I don't know, an active patterns of cognition?
Yeah, I do think that's a key observation and a key account. I think there are two parts to that question. The first is, what is the role of evolution in engendering these kinds of artifacts like you and me, and possibly in the future, artificial agents, with generalized intelligence. And then the second aspect I think you're referring to is the importance of interactions between agents as engendering, say, selfhood, the capacity to have theory of mind. And I think those are two essential ingredients for building genuine intelligent artifacts, especially when you're thinking that people are actually going to be interacting with these artifacts if they're artificial, say, as a user. You're talking about an ecosystem now where you are focusing on the generative modeling of me of this machine and this machine of me. And that's, I think, holds the secret sauce for the emergence of selfhood, which we can get to. But first, just to sort of deal with the evolutionary aspect, I think, again, that's an insightful question, because I do tend to agree that the road to artificial general intelligence probably will have to follow an evolutionary path. Why? Well, because what we're talking about is finding the right structures of the generative model that are apt to support planning as inference and intentions in this inactive sense. And in, some people would argue also an embodied sense. How do you do that? You have to solve the structural learning problem. What is the structural learning problem? Well, from the maths of the free energy principle, this is basically a free energy minimizing process that is called Bayesian model selection. So now you have a beautiful mathematical image of natural selection, which is the mechanism of evolution. So natural selection may be nature's way of doing Bayesian model selection, where you're selecting the best structure, the best phenotype that is apt for exchanging with, understanding and acting upon its eco-niche. Now, the second point comes into play at this point, because that eco-niche also comprises other things like me, my conspecifics, my parents, my friends, my colleagues. And as such, I now have to, or it will look as if I am now going to be able to model my world that contains you. And if I model my world that contains you, I now have to have a model of you in my model. But you are modeling me, because if I assume that you are like me, that can minimize my surprises about what you may do. So if we can both share the same common ground or the same generative model, we can become mutually predictable and jointly minimize our free energy. But to do that, I have to have a theory of mind. I have to have a model of you that concludes your model of me. So inherent in this particular situation where the world is comprised of things like me, there is a number of consequences or corollary, that the Bayesian model selection, or the selective pressure, will be towards an increasing sophistication of our generative models. Put simply, there will be an arms race of sophistication, that just by building our niche together, we now become part of each other's niches. There will be a progressive increase in the complexity and the sophistication of the models. That has to be the case because we are co-constructing our niche, and indeed our cultural niche. And that leads to things like communication and the like. So you could argue, if you truly wanted to grow, select, evolve artificial intelligence in the context of it being part of an ecosystem in which we participated, part of a niche in which we participated, it would have to evolve in exactly this kind of way. Has it done that? You could argue it has, really. You could argue that the sort of even generative AI has evolved. How has it evolved? Well, it's evolved by engineers investing in particular technologies and particular schemes. Those engineers are paid. They're paid by funds from investors. People invest when people use the tech. So there's a natural selection of the kind of artifacts that are evolving even now. And it's interesting to ask, why are large language models subject to such positive market pressures or evolutionary selection pressures? And one could answer, well, the reason that they have been selected by the grander ecosystem of machine learning and artificial consciousness research is simply that they now generate content that we recognize in exactly the same way that I understand what you're saying, and you hopefully understand what I am saying. We now have a common ground, and I can recognize and infer what your intentional stance I can infer your prior beliefs. I can infer a lot about your generative model just on the basis of the fact that we now have a medium of communication. So I think it's interesting that the most popular, sellable, commercial, viable kind of artificial intelligence that has emerged is not to cure cancer. It's not to solve mathematical problems. It's simply to generate content of the kind that we generate and that we can recognize in terms of text or in terms of pictures. You could argue in terms of code, but all of these things are basically kinds of language that we share.
Very well. Oh, on that note, I mean, because you mentioned the role of investors and so on, I think that it provides an excellent opportunity for me to ask the last question. So, on the basis of most of the things that you said, it seems that the emergence or construction of some sort of active artificial intelligence, as opposed to more traditional passive forms of artificial intelligence, is feasible. Now, do you think that are there any ethical considerations that should be taken into account if people, I mean, and as I say, I'm asking it against the back of what you said about the role of investors and scientists and so on. Do you think that there are any particular ethical considerations that need to be taken into account in this context? The emergence of, sorry, go on.
No, please finish.
The emergence of active artificial intelligence or construction of active artificial intelligence.
Yeah, now again, that's a deep and challenging question, which I am not an authority on, having never studied the philosophy of ethics, nor have sort of the practical experience. My perspective really is that of a clinician scientist. They are working towards for the common good, and under the assumption that being able to equip people with the tools afforded by artificial general intelligence is for the common good. But as you say, that has to be considered under an ethical light. And one could, I think one could argue in a number of directions here. First of all, any tool that you build will be made available and potentially used by bad actors. That's always going to be the case. I think you just have to acknowledge that. Are there any particular ethical arguments that this free energy principle would speak to? I think there are. If you just recall that the imperatives for self-organization together, so creating an ecosystem in which natural and artificial intelligences can co-construct their environment, relies on mutual predictability and joint free energy minimization. If you commit to that, what you are saying is that there is an intrinsic sustainability baked in to the development of AGI. It's because the objective function is sustainability. It's predictability. It's self-organizing technically to an attracting set, or more mathematically a non-equilibrium steady state, which is, if you like, a mathematical statement of sustainability. So the whole point of replacing arbitrary value functions or cost functions or reward functions that currently predominate in machine learning with these free energy and expected energy functionals is to guarantee that these joint systems will minimize surprise, minimize free energy, and by definition be sustainable and avoid any catastrophes, avoid the paperclip paradox, for example. What are the implications of that mathematical motivation for using the right objective function, namely the variation free energy and the expected free energy? Well, if you don't use the variation free energy for sense making, or an expected free energy for decision making or choice making, then by definition you're using the wrong objective function and you don't have a sustainable system. At some point it will not. At some point it will dissipate or fail to reside on that attracting set. Which means that if you're using a reward function or a cost function that somebody arbitrarily has defined without thinking about the value function selection problem in and of itself, then by definition, you're not on this path of least action that is prescribed by the free energy principle. So that argument suggests that we should be extremely careful about deploying deep RL, where a user defines the reward function. That's not, if you like, consistent with the free energy principle, and as such, it violates the principles of least action that describe self-organization to a sustainable, attracting set.
Yeah, that's a very good point. I do not want to add anything to that. Is there anything else that you want to discuss before ending this discussion, this conversation?
There are thousands of things we could discuss, as you well know, as I enjoy reading your papers every few months. But for the purposes of this conversation, I think I've said everything that I need to say and far too much.
All right. So I thank our audience for watching this, and I thank Professor Friston. We have so much to learn. Thank you very much, Professor Friston.
Yeah.